This talk then is to cover concepts in guided reconstruction and synergistic reconstruction, which of course can apply for multiple modalities, as Chris has just implied. But in this talk, I'll be focusing on the case of using MR information to benefit PET. But at the end of the brief talk here, I will cover a synergistic method where we reconstruct MR and PET data synergistically together. So with the initial focus then being on PET, why would we even want to do guided or synergistic reconstruction? Well, for PET, it's primarily noise that's the issue, though of course resolution is also an issue, and so we can seek to benefit from MR resolution as well. But one of the main drivers is noise, and so this is the kind of situation which you should be familiar with. We've got maybe quite high quality data. And then if we want to reduce scan time for the PET scan or reduce the injected radioactivity into the patient, then this relatively good quality standard PET reconstruction can downgrade quite quickly. Is that some message in the chat there? I can't see. Okay, let me know if there's something that's come up. Then if we reduce scan time or if we reduce injected dose, then we end up with noisy images, and so we need to reduce noise, and that's where guided reconstruction can really come in and help. But also we can see obviously resolution improvements that can carry across as well with guided reconstruction. So the first approach that I'm going to present to you is based on a methodology from Wang and Chi, published back in 2015, Transactions Medical Imaging. They implemented it for just PET only data based on similarity of time behavior in the PET image. But here I'll be showing it in the context of looking at MR information to see how we can use that for this so-called kernel method. It's actually extremely simple. So I'll just start off with this illustration, basically. If we consider here a standard PET image reconstruction, you will note that up till now we've been using pixel or voxel basis functions. So that means that we're representing the radiotracer distribution, this continuous function. We're approximating it, it's not exactly equal, we're approximating it by a summation of pixel basis functions. Those are top hats in 2D or 3D. And then we're basically finding a coefficient, which I'm calling theta j for basis function, bj in this case here. We're trying to estimate those coefficients in the reconstruction task. And normally we use pixels or voxels. And as a consequence, we have a lot of parameters to estimate. They're all independent, non-overlapping pixel basis functions. And if we have noisy data, then we can end up with noisy reconstructions if we just do maximum likelihood expectation maximization. So the kernel method comes in to try and modify this in a very helpful way, for example, through use of MR information. So how do we do it? Well, what we can do is say, if we're considering a pixel, a single pixel basis function, for example, in that location in the PET image, what we could also do if we have a nicely registered MR image alongside it, ideally simultaneously acquired, what we can do is look at the patch of MR pixel values within the vicinity of that pixel, which of course would look like that in the PET image. We can look at the MR image and compare the center pixel in the MR image corresponding to the PET pixel. But in the MR, we just compare all of those MR values to that center value. We just calculate a similarity. So this is what that would look like. So you can see here, we've got this kind of diagonal band of comparable grayscale values in the T1 weighted MR image. And that's why we've got white pixel blocks here showing that those pixels are similar valued in the MR image. And the similarity is just calculated in a very simple way using this, basically this Gaussian kernel, if you like. Whereas you'll see here, we've got black pixels on the edges here, because that means you can see between the center pixel value and these pixels here, there's much more of a bigger difference in the MR anatomy, in the MR anatomical image. And so those are taking on a small value of weights. So really, all you need to understand here is that you just look at an MR patch centered on the pixel of interest in the PET image, and you just get a similarity measure between all of the grayscale values in the MR. The idea then is that you could find one of these similarity maps for every single pixel in the PET image. And what I mean by that is, of course, every single corresponding pixel in the MR image, we can get this similarity map, which we then plug in as the basis function, which is going to be spatially variant throughout the entire PET image, and use that basis function, if you like, a building block for which we're just trying to find coefficients theta, to use that to replace the pixel or voxel basis function. So it's as simple as that. Just calculate similarity maps everywhere in the image and then find coefficients for them.
Andrew?
So I'll show you. Yep.
Can I ask? Edo
Yes.
Here.
Yeah, sure.
Just wondering, so do you need the PET image and the MR image to have the same sampling?
Yes. So in this example, excellent question, Edo. Yeah, these are assumed to be on the same gridding, so you can resample the MR image onto the PET. Yes.
Would you do that or the opposite?
So here, I think this is a long time back. You can see it's 2016 now. Here, I think we did it that way around, but there are, of course, options available. I mean, what one could imagine doing is you could visit every single pixel location in the PET and then look up that exact coordinate in the MR. And then for each of the neighbors in the PET pixels, you can just look up those coordinates in the MR. But you raise a very interesting point, Edo, because I did do some work with Martin Belzunce where he did look at trying to make use of higher resolution MR. So here in this slide, what I'm conveying, hopefully, that's hopefully quite clear, is the concept, and the kind of question you were asking, Edo, is absolutely spot on, because you're realizing there are many possible ways of doing this. So one could be inspired, for example, I guess this is where you're going with your question, one could be inspired to do PET reconstruction at the MR voxel gridding kind of resolution. And again, in fact, I have done some work on that in the past, and maybe I should have included that in this presentation, but this is some of my very early work when I was still in Montreal. But does that capture the question, Edo? Or?
Yeah. So I don't know. I mean, it does answer my question. It opens new, so it's okay. Go ahead.
Yeah. But hopefully the concept is crystal clear, and there are, of course, an infinity of ways of generating these similarity maps, and you can do them at the MR resolution, you can do them at the PET resolution, but you've got all the usual catches and concerns that you might worry about if you start trying to get to MR resolution with PET quality data. You can end up building in misleading features into your PET reconstruction that are just simply, not present or sustainable from the PET data. Yeah. No, excellent question. Please, anyone else, do feel free to put questions in the chat as we go along. And in fact, Edo, maybe you can keep an eye on the chat and feed through any questions live. That'd be very helpful.
Yeah. I'll interrupt you with no regrets.
Okay, fine. That works. Great. Okay, so hopefully this slide is fairly clear. In terms of just saying we're replacing pixels with these kernel basis functions. But the methodology that you've just seen in the earlier slide is kernel EM. And so sure enough, the way this is done in practice is just using MLEM, maximum likelihood expectation maximization, or ordered subsets EM. So this is the standard algorithm. In previous talks, I've been using X for the image. There's one subtlety here now that I'm using theta. These are parameters that are, if we're dealing with pixels, are just the coefficients or amplitudes for pixel or voxel basis functions. And so you'll remember this algorithm is just forward projection, ratio, back project, multiply. But to do kernel EM, all we do is just a linear model. We just use a basis function matrix. So now we've got, so the matrix B here would have been the identity matrix up here. So theta times identity, forward project, and so on. Here, instead of the identity matrix, we now have those clusters of similar MR pixels grouped together in each of the columns of the matrix B. And then what we're doing is finding the coefficient vector theta, which would weight all of the columns of the matrix B, sum them all together to produce an image, which when forward projected via matrix A and adding on scatter and randoms needs to match the measured data. So that is all that is going on. Hopefully that's clear, otherwise I'm sure Edo will interrupt. Okay, so if we do that, just to demonstrate the concept here, this is for when we're reducing injected dose in PET imaging. This would be 100% dose level, maybe that's of the order of 240 to 370 megabecs. Then as we thin the data down, simulating low injected doses to, for example, just 1% level injected dose, and the big inspiration there is we want to get injected dose levels of radiation dose received by the patient down to a transcontinental flight level. So that's a really low injected dose. If we use pixels, we get this kind of behavior. And if we use the kernel method that I've just talked you through using MR information, then you can see that quite impressively, image quality holds up quite well. It's probably worth pinging random values at these basis functions just to show to what level the MR information has kind of been hard baked into the solution through that basis function matrix. You know, here, if you put random numbers in, you'd literally get a completely random image. Whereas here with these basis functions, even with random numbers, you'd probably get something remotely resembling to the MR. So just to demonstrate a point there. And in fact, that's like a nice introduction to deep learning and GANs and generators where, you know, with GANs, for example, you ping random numbers into sample from a different distribution. Here, this is like a linear generator, if you like, a matrix B that you could just fire random numbers at to get all kinds of samples of possible images that use MR basis functions. Anyway, so you can see the power of the method in this slide, I hope. So going on from kernel EM. So kernel EM is you just take OSEM, plug in a basis function matrix, and you're good to go. Another way of doing it is to use those kernel values within your penalty function for a least squares reconstruction, or within your prior for a log posterior, maximum a posteriori reconstruction, which is typically the case in PET. So let's see how we can embed those kernel values into a regularizing prior instead of hard baking them into the basis function matrix. So you remember from last week, we had something like this. I'm just using theta now instead of X. So remember, we could look at, for example, pixel pairs within some neighborhood. And we've got some energy function that we want to be small in the reconstructed image. So here we're expecting pixels that are nearby each other to be similar valued. If they're similar, that will give a low energy. If they're noisy, if they're very different, this will give a high energy. So what we do typically is we take the square of those differences for a quadratic Tikhonov style penalty, or if we took the absolute value of those differences, that would be total variation L1 norm, because of course we do need to sum them all up as well. Just a reminder that of course we could build in some kind of weighting factors here that compensate for the fact that if these are far apart, then we can switch off that penalty, we can reduce it. So I'm showing here reduced weighting factors with increasing distance of the pixel theta c from theta j. And then we have to consider this, of course, for all the pixels in the neighborhood, and then we have to consider it for every single pixel with its neighborhood in the entire image. So that's where we were before. And now what I'm going to show is that we can modify that by putting in a weighting factor kernel here that's directly the same as the kernel basis functions that we've just been looking at. So instead of now using them as clusters of pixels or voxels as basis functions, instead we're now going to use them as weights that can modulate the impact of that quadratic or that absolute value total variation penalty. So let's take a look at what that would be. So it's very similar to the earlier slide. So we're looking at a pixel in the MR image. We're doing a similarity comparison with all the pixels in the MR. This is what a similarity map might look like. And you notice we've got these kind of continuous valued weights. These could be typically 1 if things are identical, or 0 if they're completely different. And so this effectively, as I've said, modulates or switches on and off that penalty function. So it would mean concretely that if you can see here, MR anatomy is similar along that diagonal, but different in that direction. So because MR is different in that direction, that means that pixel to that pixel, we will be switching off the quadratic penalty in that direction, saying, no, it's perfectly okay to have a difference in that direction. That's got no impact. That is perfectly fine for our reconstruction. Whereas in this direction, if there are pixel differences, then the penalty would still be alive. And so we'd be encouraging smoothness along that direction and permitting differences in that direction, for example. So that would be the kind of general way of doing it. But you've probably heard of the Bauscher method, the Bauscher guided penalty for map reconstruction. If it's the Bauscher method, then very simplistically, we're effectively doing something like K nearest neighbors, where we're either within the group or we're not. So this is saying, based on some threshold, which is determining how many nearest neighbors, if you like, we can, okay, Edo, question?
Yeah, there is a question in the chat.
Go for it.
From Giovanni Di Domenico. He says that PET and MR have they are based on different physics, of course, and he's asking why the WCJ must be the same.
Yeah, so that's an excellent question, and in a few minutes' time, I'll be covering the case where things are different. So the a priori, well, the assumption we're making here is that that the PET tracer distribution is going to be smooth, not rapidly changing necessarily within particular anatomical regions. And so, for example, imagine you've got a gray matter, white matter interface, which, you know, for example, is between here and here or here and here. Then it's maybe a reasonable assumption. Imagine you're doing raclopride, looking at chordate putamen and so on. You're not expecting, you know, raclopride, for example, to be leaking out into the surrounding white matter. So it is an assumption that's being made. You know, any prior, we are building in assumptions, and you've absolutely got to scrutinize those and consider whether or not they're valid for your particular application. But it's absolutely a spot-on question, and it is one of the assumptions. But I'll show you a way of trying to counteract that to reduce that level of assumption in a moment. So at the moment we're saying, yeah, if it's similar in the MR, we allow similarity in the PET. But notice, you know, you can still get differences even in this region in the PET. If the PET is very different here to here, then it will still allow that. It's just that we're applying a quadratic penalty in that direction. So if you're happy with a quadratic penalty, then there should be no issue with this. It's just that we'll be imposing a bit more structure by guiding the smoothing and switching off in a different direction. Anyway, good question. So the way we do it is the same as what I presented last week. So there's our quadratic penalty with now spatially variant weighting factors based on that similarity map from the MR image. And so the method I talked you through last week, I won't repeat it in great detail now, other than to say that basically you do a guided smoothed update. So at any given update, you've got a theta k for your parameters. Consider them as just pixel values if it helps. And in fact, for this case, there will be pixel values because this is now a guided penalty. So we're staying with pixel basis functions, but we're just doing the penalty method instead. And what that says is do a guided smooth. You do WJL theta L. That's doing a neighborhood averaging. And remember, W could be 0 across boundaries. So it will not smooth across boundaries, but it will smooth within uniform regions that are value of 1 in the Bauscher prior. So that's the guided smooth. And then you just add on the previous estimate. That's just an optimization necessity for the De Piero method. And to cut a long story short, the update is basically the familiar EM update, forward project, ratio, back project, multiply, divided by a combination of the guided smooth with the standard EM update. So that is all that is happening. The kind of results, I showed this slide last week, that you'll get will be something like this with the Bauscher prior, where these W's are either 1s or 0s. If you use large similarity clusters, in other words, we're not really imposing much in the way of boundaries, then you can obviously end up doing a quadratic penalty in large regions, and you end up with a very conventional smooth image. But as we reduce the number of, if you like, something like nearest neighbors, in other words, reducing the size of those similarity clusters to be more and more restrained and constrained to the anatomy, for example, following the edges of the gray matter, then indeed what happens is we end up only doing smoothing preferentially in regions that are similar in the MR, and we don't smooth across regions that are different in the MR. And that's why we end up with this kind of noise reduction with apparent edge enhancement based on similarity of the MR. Okay, so now, and this kind of touches on that question that just came up. There are issues with what I've just presented because, for example, if the PET has a very unique uptake in a particular region and there's no such anatomical kind of correspondence to that, then we'd be at danger of smoothing that out. And so let's see now how we can try and preserve PET information whilst benefiting from the MR information as well. And so this is the so-called anato-functional. So in other words, previously, if you like, it's just anato based on T1 weighted MR, but now we're using the PET as well to influence those clusters or those guiding weights. And so this was published by Abfaz Morini in 2017, Physics, Medicine and Biology. So this is what happens. We have exactly what I've been showing you before. We look at a patch in the MR, but now we also look at a patch in the current update of the PET reconstructed image. And all we do is calculate the similarity map here, calculate the similarity map of the PET, take them in product, and therefore if there's a particular unique feature in the PET, then we kind of use that as a self-guidance mechanism in the calculation of these weights. So these weights now will try and preserve similarities that have begun to show up in the PET, whilst also modulating them with the similarity map from the MR. So this is like a conservative similarity map. In other words, it will rapidly drive towards less and less areas where we're permitted to smooth, because it'll try and keep features that are in the PET and features that are in the MR as well. And so just taking the product of those similarity maps, we can use those as the weighting factors for our, for example, quadratic penalty function. So if you do that, this is not the best example slide for showing that off. I'll show you one later that gives that concept a bit more clearly. But again, we just get, as expected, look at the bottom row here, at 1% dose level with MAP-EM PET-MR guidance, we get a result like this compared to MLEM, or a result like this one compared to MLEM. So it does appear to help. Now, kind of going back to where we started, remember we started out with kernel EM based just on MR similarity maps. And I've just explained to you that we can put those MR similarity maps into a map penalty. And then I've also just shown you that we could include the PET similarity map in product with the MR similarity map in the regularizing prior. Yes, Edo? You need to unmute.
There is another question asking if these methods have been used in PET-CT or SPECT-CT as well as PET-MR.
That's an excellent question, which I'd rather defer to Chris or others, because my experience of the literature is in PET-MR. I think very early on, there were methods with PET-CT, but of course the problem with, for example, CT of the brain is you've got very little contrast coming in there, and so the guidance information isn't necessarily as useful. Sounds like Gail's going to have a comment here.
Yeah, so that's the point, right? So if you want to have a nice anatomical prior, you need contrast between your structures of interest. Yeah. But for example, there is a commercial product by Siemens in their SPECT-CT systems where they have a SPECT bone tracer. And of course, in CT, you have excellent contrast between bone and surrounding tissues. So there, this anatomy guided reconstruction is also used. So as long as you have contrast in your anatomical prior between the structures of interest, you can use, well, other prior images.
Yeah, that has been used also in the thorax, for instance, for aortic aneurysms, because again, the aorta you can see very nicely on the CT, certainly. So if you have contrast, and obviously a lot of the methods here have been used for dual energy CT, so and in MR. But I'm not aware of the extension of Abfaz Morini methods being used in other modalities, but
okay, well, yeah, so just to explain on that one further, we did publish arterial spin labeling reconstruction using T1 weighted MR to guide the ASL image reconstruction, which is a very obvious, relatively safe application of these kinds of methods. And again, a bit like Chris said in the outset here, what I'm presenting here is the concept. I'm not at all advocating use in any particular case or another. That's over to you and your choice of risk of assumption. But there are obvious ones where it's safe. You know, I'd feel like, you know, doing T1 weighted guidance for a T2 reconstruction is possibly fairly safe. Certainly is for ASL, maybe fMRI as well. So I'm conveying concepts here. I'm not advocating particular applications. But in fact, also recall what Chris said earlier as well about low dose, high dose. One could argue, if you're in the unusual situation of having high dose PET, or indeed the original kernel method of Wang and Chi, what they were doing was looking at 3 time frames and building those so you get a time activity curve, if you like, at 3 time points for each PET voxel. What you can do is look at the similarity of those time activity curves. So that would be then using the entirety of the PET scan as guidance information for reconstructing, for example, 1 time frame of the PET scan. So there are safer ways of building these similarity maps than the kind that I've been showing here. Right. Okay. So what I'm doing now is going back full circle to the beginning where I mentioned kernel EM, and just to point out that Data et al. Basically put the PET information alongside the MR information for the basis function. So remember, kernel EM that I presented earlier was the MLEM algorithm, now with a basis function matrix B. And if you remember before, all we used was the MR similarity to generate the basis function matrix. With the so-called hybrid kernel EM method, what they did was to use the current update of the PET image to calculate the similarity map. And of course, there are many ways of doing this. You know, I'm showing it here as a simple product, but you could use a kind of a longer feature vector for the comparison here in your similarity map. Whatever way you choose to do it, you can combine PET and MR information into a similarity map and use that uniquely calculated every single pixel in the PET image to generate your basis function matrix. And then you're just doing MLEM to calculate the coefficients, except of course here with hybrid kernel EM, you're going to have to revisit the definition of your matrix B based on your current PET reconstruction. So the frequency of update of that basis function matrix is obviously a key question here. Okay, so just to finish, I'll touch on some of how we deal with some of the issues. Georg.
Just a short question, Andrew. If we update this matrix B after, let's say, every iteration or every whatever, is that scheme converging? Because we are basically changing the basis. Sure. So it's not obvious to me that this is converging.
No, well, it's not obvious, but you could argue that for any fixed basis function matrix B, you have now defined a convergent EM algorithm. But then what we're doing, or and this is not a method I've put forward, is it Daniel's method, I think. Then what he's doing, you know, at any given point, you've got a convergent algorithm, but he's just changing the objective function. In other words, changing the system model, because your effective system model here is now BA. And so if you're changing your system model, you're changing your objective function at every update. So it's like you're kind of moving to a new solution. Then we go, oh, but actually now the objective is here. Now we're moving objectives there. And the question is that you're posing there is, do you end up with an objective function that settles to a fixed objective function that you can finally head towards? And that's a great question. I'm not going to claim to be able to answer it, but conveniently you could say at a certain point, right, I'll stop changing B, and now I do have a maximum likelihood method that will converge.
Okay, thanks.
Okay, so synergistic reconstruction tries to be a bit more elegant than the methods that I've just been touching on up to now. So this is work we published in Magnetic Resonance Medicine back in 2019. Following on, we're not the only ones that have done this. Matthias Erhardt has done work here, for example, as well. I know Chris has been involved in work like it. So I'm just presenting, if you like, a personal perspective based on work I did with Abulfaz Marinian. And so what we have here is the objective function. Remember, we talked about that, of course, you're familiar with that from last week. We have the PET Poisson log likelihood expressed as a distance measure. Crudely, you can consider that as an asymmetric distance, the KL divergence. And then we've got the Gaussian log likelihood, that's the least squares distance. And then we've got now a penalty function, which is a function of both the current MR and the current PET image. So these feed in fact, to be clear, K here doesn't mean iteration number, it means a particular contrast. So this could be T1 weighted, T2 weighted, flare, ASL, well, whatever it is that you've got, your whole series of parametric MR images. And here we just got one PET image U. So that superscript K is talking about the contrast, if you like. And so now we have a joint prior that's based on your PET image and up to, for example, here, M different MR contrasts. So for the PET, we've got the familiar system matrix with all the positron range, forward projection, attenuation, normalization, et cetera, And now E is our overall Fourier, or our overall encoding matrix for MR for the kth image contrast. So that would be coil sensitivities, discrete Fourier transform, and then undersampling, or your k-space trajectory, if you like. It's just leaving behind the k-space values that you're measuring in that acquisition. So that's the joint objective function. And the key in the joint objective function for synergistic reconstruction is, of course, not in the likelihoods, it's in the prior there. So we're just going to look at the prior. And it should be fairly easy to understand based on all the stuff I've just been covering. We've got, if you like, a weighted quadratic difference penalty here. There are the weighting factors there. And then like for the PET, we've got exactly the same for each of the MR contrasts. So contrast K equals 1 to M. We've got exactly the same penalty function that we've been looking at all along in the context of PET, but now applying it to MR as well. How do we get, so the key thing here is going to be the weighting factors that modulate that quadratic penalty, that finite difference, and then L2 norm, if you like. So what happens is we take the PET image at any given update, we calculate the similarity of values along the lines of what I've already been showing several times now. And then for a given MR contrast, we can also do the same, find the similarity map for a particular pixel as well. And in fact, we can do it for all the K contrasts. And then we can just multiply those two similarity maps together. And so here I'm showing it for the PET similarity map. MR contrast 1 could be T1 weighted MR image, all the way up to the nth contrast. We multiply all those together to get an overall weighting set of weighting kernels. Here they're called omega, but W is what we've been using up to now. And these effectively modulate the penalties. But notice they're based on both the PET and MR here, and they're based on the PET and the MR here as well for both the PET and the MR penalty functions. And so that's why we've called it mutually weighted, because these are mutually weighted, self-evident. Okay, the methodology is, it'd be great if someone asks me if this converges, and I'll defer on that along the lines that I answered with previously. But what we can say is any given update, we do have a well-defined problem, but then we go and change the weights, change the prior, and so we change the objective function. But anyway, let me talk you through it. Basically, it's the MapEM methods. This is the good old EM update, PET image U, forward projected, etc. Regularization is just now what we've seen before, just written slightly differently here. It's basically the EM update with this thing here. And you need to just focus on what this is. This is basically that guided smoothing operation that we've seen before for MapEM. So the update is the EM update in fusion, if you like, in combination with a guided update, where the weights for the guided smooth come from that product that we've seen earlier. And obviously it's going to involve resampling, and that takes us to Edo's question earlier on about how we do the resampling. And there's obviously more than one way of doing it. But I think here we were resampling onto the modality that we needed to reconstruct from. So that's how you do basically you do 2 updates, but of course this is an open question as well. How many updates do we do of the PET image? Anyway, here 2 iterations were done. Then the PET image is held constant. And then what we do is a couple of iterations, for example, of conjugate gradient, gradient descent, whatever your favorite approach is, where what we're showing here is this is just the least squares problem, just written as the normal equations. So I refer you to the talk from last week. This is the solution for the MR reconstruction, where we're just basically seeking to invert. This is like A transpose A, and this is like the Tikhonov penalty. Here are the weighting factors. This is the finite difference. So that's a weighted guided quadratic penalty. So just like what we've been doing for the guided smooth here, but built into the least squares context. And of course, we don't solve that in one go. We do it with an iterative algorithm. So conjugate gradient or a few steps of gradient descent will be fine. So you get an MR updated image with a guided smooth. And then finally here, we take the product of all the similarities to recalculate those weights to then go back to do a couple of updates to the PET, a couple of updates to the MR, recalculate the weights, and around you go in this kind of alternating optimization pattern. If you do that, now this is the rationale for doing that. Just let me show the kind of problem that was suggested earlier by saying, well, can we say the MR is going to be useful for PET when things are actually different? Well, let's see what can go wrong and how this method can fix it. So here is a T1 weighted MR. Here is a ground truth. This is simulated data. This is a ground truth PET. This is a conventional MLEM reconstruction with low counts, as we've got the noise problem here. This is just a MAP-EM standard regularized PET reconstruction, total variation used here. Now, if we do conventional guided reconstruction, this is the kind of problem that can happen. Notice this has got a unique PET lesion in the ground truth. So it shows up quite nicely in the standard regularized PET only reconstruction. But because that lesion is absent from the T1 weighted MR, T1 weighted MR says, yeah, go ahead and smooth in that region there, no problem at all. And if you come over here, then what's happened is that PET unique region has now adopted MR structure and is clearly very distorted. Whereas the method I've just shown you, the synergistic reconstruction with the alternating updating of the weights, and even the anatofunctional method that I talked about earlier would have benefits comparable to this. We can now see that by embedding the PET information with the MR information in the calculation of that joint prior, then we can preserve that PET unique region whilst also getting the MR benefit elsewhere. For real data, this is just a quick anecdotal slide to finish on. For synergistic PET-MR reconstruction from real data from the MMR scanner. This is the fully sampled reference for MR, first of all. There's no reference for the PET. We didn't do a super high count reconstruction here. Then we've got the sense reconstruction from undersampled MR here for T1 and for flare. And this is the low count PET. Then if we do conventional modality specific regularization, so if we did total variation sense for MR, and if we just did MAP-EM with total variation for PET, we might get a result like that. And then if you do that synergistic method that I've just talked about, then you begin to see some benefits. And of course, the method does apply for, as we've implied, for reconstructing different contrasts in MR by using all the other contrasts to help guide the reconstruction. So that's all I wanted to present in terms of concepts of guided and synergistic reconstruction in the context of PET-MR. I'm happy to take any questions before handing back to Chris.
I have a question, and nobody else has. So you never take any fully sampled MR, I guess. That's why you want to update MR reconstruction as well?
Yeah, so in other words, what your question is, what is the synergistic benefit for MR? I guess that's your query. Is that what you mean? Yes, I mean, yeah. If we've got fully sampled MR, then yeah, one could argue what more do you need? That's good enough, right? So but as you know, just like with PET, the problem is noise. With MR, the problem is acquisition time, and so there's often the need to undersample the data, and so you need all kinds of regularization strategies to compensate for the aliasing artifacts that would.
Yeah, I was thinking more mundane at the fact that you were doing a conjugate gradient update on the MR, and if you have fully sampled, it's just you don't need to do it many times, right?
Right. So in fact, I think. Whilst I think it was published mentioning conjugate gradient, or at least in this presentation based on the conference presentation, I think it's almost wiser to not go too fast. So just a couple of Landweber-based least squares updates with modest step sizes are probably a safer way to go. This is the problem with this alternating approach. It's a bit like, the big issue there is, well, do we do 1 iteration, 2 iterations of PET? Do we do 1 or 2 of MR? Because, for example, if you go and do 100 conjugate gradient updates for the MR, you've got your you've got almost your conventional independent MR reconstruction with aliasing artifacts imprinted, which you'll then carry through. So there is definitely a risk. Yeah, you're absolutely right. The idea here is to go slow and ease our way in towards finding this joint objective function. And yeah, again, we've got the moving solution, and we've got the moving objective function, and we hope that the two kind of meet eventually one day.